Welcome everyone to our USACM Energy and Earth Systems Technical Thrust Area webinar series. So just a little bit about the Technical Thrust Area, or TTA. So my name is Irina Tazaur. I'm the chair. We have Steve Sun from Columbia as the co-chair, and two other members at large who are members of the leadership team, Clint Dawson and Yuri Bazilevs. And basically, the technical thrust area covers a variety of different topics, from climate and earth system modeling to climate couplings, geomechanics, different types of energy, carbon sequestration, capture, storage, oil, gas recovery. And if you're a member of USACM, it's free to join. If you're not a member, becoming a member gives you discounted registration on various USACM conferences and workshops. So I would encourage you to join. If you're a member, you'll get announcements about this, every time we have an activity. If you're not, you can follow our LinkedIn page, where I also post the webinars and other announcements. So this is our second talk in our Spring 2026 webinar series. I'll introduce the speaker shortly, but we do have 4 more speakers coming up who are listed here. So basically one a month. If you're interested in any of these topics or know the speakers, please try to attend. We've had pretty good attendance overall, which has been great. So let me stop sharing, and maybe Rebecca can share. And while she's sharing, I'll introduce her. So today's speaker is Rebecca Gjini from UC San Diego. So Rebecca is a 5th-year PhD candidate in the Institute of Geophysics and Planetary Physics within the Scripps Institute of Oceanography at the University of California, San Diego. She previously received her Bachelor's of Science in Mathematics from Lehigh University. Her current work focuses on derivative-free parameter estimation and uncertainty quantification for understanding the climate system. And her advisor at UCSD is Matthias Morsfeld. And I'll also mention, I believe Rebecca is looking for jobs for when she graduates soon. So if you are hiring and you like her work, please reach out to her with any opportunities that you may have. So with that, the title of the talk is the Ensemble Kalman Inversion Race, and I'll go ahead and hand it over to Rebecca.
Okay. Yeah, thank you so much. And I am currently looking for postdoc positions. So if you like this work, please reach out to me. I have on the last slide of my presentation, I have my email. And I can feel free to reach out to me or Google search me, and you can also see my contact information. But without further ado, so my name is Rebecca Gjini, and I'm very excited to talk about my work on the Ensemble Kalman Inversion Race. And quickly before I begin, I'd also like to thank my collaborators, my advisor, Matthias Morsfeld, who's with me at Scripps, and then my 2 other collaborators at Caltech, Oliver Dunbar and Tapia Schneider. Um, so the way this presentation is organized, I'm first going to go through the introduction and motivation of this research. Then I'm going to go into the basics of ensemble-based optimization, go through one of the algorithms, and then talk about the different types of ensemble-based optimization that we look at in this work. Then I'm going to talk about time average data and the convergence criteria that we use for each of these optimization algorithms. And then I'll go into some example problems that we use to test each of the methods. And at the end, I'll summarize and conclude our findings. Okay, so the main motivation behind this work is we really want to try and improve future climate predictions. And one way that we can do this is by calibrating global climate models, which I'll refer to as GCMs, using Earth observations. And when I talk about global climate models, I want you to think of them as having 2 components. The first is what are called the dynamics, which include solving the Navier-Stokes equations on a grid. And then we have what are called the physics parameterizations. And within these parameterizations include all the processes that we can't resolve on the grid scale, for example, like cloud microphysics. And these can be parameterized either by physics, um, either with physically informed parameterizations, or we can use machine learning architectures like neural networks within these parameterizations. So this is the two different ways, and we want to be able to include both. So we're kind of living in this hybrid approach to climate modeling. So a promising approach to GCM calibration is to estimate the parameters from observed climate statistics. And I'm going to go through exactly how this approach works. So within these physics parameterizations, so if I consider our GCM as our forward simulation, it relies on these input parameters, which can either be physics informed parameters within our physics parameterizations, or they can be AI parameters like the weights and biases of a neural network. And when we input those parameters into our simulation, then we can run our GCM for a certain period of time, and then we'll get out these model trajectories. And so as an example, uh, I have some trajectories of temperature over a given time window tau. And so from these simulated trajectories, we can calculate some statistics. So we can define a statistics function. For example, maybe we want to take temporal statistics over this time series. And then we can calculate things like the mean and covariance or first and second order moments. And so this is what we're trying, this is like the entire forward process of this. So we're taking our input parameters, and from this entire process, then we're going to get out some modeled climate statistics. And what we really want is we want our model parameters to minimize the misfit between the modeled and observed statistics. So this is really the goal that we're after. But there are many difficulties with doing GCM calibration, and I want to highlight a few of these. So the first is that GCMs are very computationally expensive. Um, they can take many days to run one simulation on a supercomputer, and because of this, it makes it really difficult to execute some calibration algorithms. The second is that there's typically no derivative information, and there's actually quite a bit of work that's been going in this, especially with all the auto-differentiable tools that are currently coming out. But for this work, we're going to assume we don't have derivative information to help in these problems. But even if we did have derivative information, we're also dealing with an extremely noisy loss landscape. And so what I mean by this is if we were to look at the loss, which is the misfit between the modeled and observed statistics for a given parameter u, we see that there's all this noise within our loss function, which makes it really hard to optimize over. So if we were to start at a given point where the yellow dot is, um, if we were to use derivative information, we would probably fall immediately into a local well, and then we wouldn't get to where the true global minima is. Um, the next issue is that we're working in a high dimensional parameter space. We're dealing with hundreds to possibly thousands of parameters, which makes the scalability of calibration algorithms really difficult. And then the last thing is that statistics are indirect observations. So because we're in this hybrid setting where we might want to include some machine learning parameterizations, we don't necessarily have a lot of input-output pairs that can help us represent that process. So we need to be learning these machine learning tools more in an indirect way. And so this is where the ensemble-based optimization comes in. The main idea is that they can approximate derivative information using the statistics from an ensemble. And they have many benefits, one being that they're derivative free, so we don't need the adjoint information in order to use them. And they have the ability to smooth over noisy loss functions or uncover the true structure of the loss. So what an ensemble-based optimization algorithm might see is this kind of smoothed over true like underlying structure of the loss function. So again, if we're starting at the same yellow dot, it would be able to get to the true parameter, the global minima of U. And so there are multiple ensemble-based optimization variants. And so the main question of this work is, well, which ensemble-based optimization should we use to estimate parameters from time average data? So next I'm going to go into ensemble-based optimization, and I'm going to go through one of the algorithms that we use in detail, and then I'm going to talk about all the different optimization methods that we compare in this study. Okay, so the main goal in optimization is to find the parameters u that minimize the loss L. And so the loss function that we're looking at here is going to be the weighted data model misfit, where in this case, G is our nonlinear model that takes our parameters u, which can either be AI or physics-based. And when we put those into G, it's going to run our GCM, and then it's going to output some statistics, which we can compare to our observations Y. And then lastly, we have our observational covariance matrix R. And I'll go into more detail of exactly how we calculate R for each one of our example problems. But for now, this is our general setup. And so in a typical optimization algorithm, we would start with maybe a guess at the parameters UK, and then we add some update to it, which depends on the step size alpha and the search direction at each iteration, which would be delta K. And then we can add this to make an updated guess UK plus one, and then we continue to iterate. And so here I have a little cartoon of how in a 2D space we might propagate through a loss landscape in order to get to the global minima. Okay, so next I'm going to go into one of the ensemble-based optimization methods that we use, known as Ensemble Kalman inversion, which I'll refer to as EKI. And again, the main idea here is that we can approximate derivative information using the statistics of an ensemble. So I'll leave, again, the problem setup in on the slide. So the first step is that we're going to define an ensemble. We're going to define our initial ensemble, which will be different parameter choices. So we'll have any ensemble members, and then we can take each one of these parameter vectors and we can run it through our forward simulation G to get then an ensemble of model output vectors, which will be little g. And so from these ensembles, we can calculate ensemble perturbations. So first we can take the average over our parameter ensemble, and then we can subtract it from each ensemble member, and that's going to give us our ensemble perturbations. And we can do the same thing for our model output ensemble. And then from this information, then we can calculate covariances from the ensemble members. So we can calculate the cross covariance between the parameters and the model output. And then we can also calculate the covariance of the model output ensemble. And then using these covariances, we calculate the update for the optimization algorithm. So in this case, our UK plus one is going to equal UK plus our update, which includes the two covariance matrices. And then we also multiply it by the difference between our observations and each one of our model output ensemble members. And a quick note, we do update each ensemble member individually, so each ensemble member gets a slightly different update based on what value its model output vector is. So this is the EKI algorithm, and to showcase how this algorithm works, if we're looking at a 2D parameter space, and the contours are representing the loss landscape, on all the teal dots are showing an initial ensemble. If we were to iterate over this algorithm, we see that the ensemble members immediately collapse onto each other. And so in all these methods, this is the nature of how we know where the optimal point lies, is that all the ensemble members will collapse onto each other, signaling convergence of the algorithm. Okay, so there are many different variants of ensemble methods for optimization, and I'm going to talk about the ones that we use within this study. So the first one is called Tikhonov regularized EKI, or TEKI. And this algorithm is exactly like the one I had showed before, but in this particular case, we take our observational covariance, our observations and model, and we're going to stack that on top of our prior information. So we have a prior mean and covariance. And this allows us to integrate regularization within the loss and the optimization algorithm, so we can optimize over a regularized loss function. And then I'll note here that for the remainder of the algorithms, we also include the regularization in this way. So each one of the methods is solving a regularized problem, and so they should be targeted at all the same solution. The next method is known as the iterative ensemble Kalman filter, or IEKF. And this one, if you're familiar with the ensemble Kalman filter, it's very similar, but in the ensemble Kalman filter, we use the Kalman gain to make an update, and we include a different set of observations every time we make an update. But in this case, we're just going to be assimilating the same observations every time. So we're not including new observations, but we're using again that same Kalman gain update. The next one is called Ensemble Transform Kalman Inversion, or ETKI. And this method is based off the Ensemble Transform Kalman filter. And in this particular case, we're making an update in a transform space. So we can think of this as we have our ensemble perturbations matrix, UK, and then we are able to calculate what's called the ensemble transformation matrix T to transform our ensemble perturbations into our updated ensemble. And so that's how this algorithm works. And then the last one is what's called unscented Kalman inversion, or UKI, which is based off the unscented Kalman filter. And in this particular case, the idea is that we purposely pick each one of the ensemble members so that they represent the first and second order moments of the distribution. And for UKI, the number of particles that you need to have is always going to be 2 times the size of your parameter space plus 1. So if we're looking at a 2D parameter space, we would have 5 ensemble members. And as you can see, they kind of take this plus-like configuration to capture the first and second order moments of the distribution. And as they update, they'll make an update, and then they'll update the mean and covariance of then the updated distribution, and then the particles will get reinitialized. And so this is how this algorithm works. And lastly, uh, the last method that we use to compare to these ensemble methods, we use a classic Levenberg-Marquardt optimization algorithm just to really showcase why these ensemble methods are so powerful and why they're really the right choice for this type of problem. Okay, so now how are we going to evaluate each of the algorithms? Well, first we're going to define a target error, and we use the root mean square error. And I'll go into a little bit more detail about this in the next section. But essentially, we want each of the algorithms to reach the same level of accuracy in order to determine what their computational costs are. And then we will identify an optimal ensemble size. So aside from UKI, each of the other methods can have varying ensemble sizes. So we're going to pick the optimal one and use that to compare to all the rest. And then lastly, we're going to count the number of forward model evaluations each algorithm takes. So in GCM calibration, running your GCM is very computationally expensive. So we want to reduce the number of evaluations that we have to do. And so we really want to see which algorithms require the least number of forward model evaluations to hit the same target error. And then all the experiments or example problems that we have explore the relative cost, scalability, and generalizability of the ensemble methods. Okay, so next I'm going to go in a little bit more detail on the time average data and RMSE criteria that we use for each of our example problems. Okay, so with the time average data, I first want to talk about, well, why are we using time average data? The 2 main points I want to talk about is, one, sometimes we're limited by only having statistical information. If we're thinking about doing GCM calibration for the climate, we might only have statistical information of the climate that we can use as our observations. But then even if we did have trajectories, it's actually very difficult to match trajectories because of the chaotic nature of the atmosphere. It's very easy for our model to deviate away from the observed trajectories, and this makes the problem much more difficult. So this is why we're using time average data. And so again, I'll put up this graphic of we have different trajectories over a given time period tau. And so we take what we call a feature-based approach to extract information, sufficient statistics from this in order to then perform the optimization. So from this time series, we can calculate some statistics. So we define a statistics function S, and then and as an example, we can take the mean and covariance of this time series or first and second order moments, and we can use that as our observations. And so the next point I want to talk about is that the noise level of the statistics depends on the length of the simulation that you run for. So if we were in a perfect world and we ran our simulation for an infinite amount of time, the initial condition that we start with won't matter. It won't get considered within the statistics that we calculate, so it has no effect. However, we're never able to infinitely run our simulation, so we're always in this finite time domain, and different initial conditions do generate random Gaussian noise within our estimate of within our estimates. And so so the longer we run the simulation, the smaller the noise that we generate because it's closer to the infinite in the infinite case. But the shorter the time window, the larger the noise is going to be. And so then we can kind of rewrite our loss function like so. And as you'll notice, we have this R matrix in here. So I want to talk about how we calculate the observational covariance matrix. So again, if we're looking at a model output time series, instead of running just for a period of time tau, we can run one really long simulation for n times tau length, and then we'll have these little windows of time tau. So from time 0 to time tau, that's one window, and then from tau to tau 2, that's a second window. And then from these windows, we can actually calculate statistics over each one. So we can calculate a mean and covariance for each of the time windows that we have, and this is going to give us n samples. And then from these samples, we can calculate our R matrix. So we can determine what the variability of the system is based on this really long time series. And so for each of the example problems that I'm going to show in the next section, we use this method in order to calculate the observational covariance. Okay. Lastly, I'll talk about the algorithm evaluation criteria. So we want to be able to determine how well each algorithm solves the optimization problem. And in typical optimization, we might want to check the solution after convergence within a specified tolerance. For example, how close our previous guess at the parameters is to the current guess at the parameters. But this method is not great because we can't compare each of the solutions that they find because then they'll be at different accuracies. And so what we really want to do is we want to stop iterating the optimization algorithms when we hit a specified target error, so then we can so we can determine the computational cost of the different methods. So each algorithm is going to have to reach the same level of accuracy, and then we're going to count the number of forward model evaluations each method needs to reach this target error. And so the target error we define is the root mean square error, which is the calculated data model misfit, and it's weighted by the assumed data errors from that observational covariance matrix. And so then we also have to determine what ensemble size we should use for each of these methods. As I said before, some of the methods you can pick the ensemble size, so we need to know, okay, well, which ensemble size are we going to use to compare the methods? So here's a plot showing number of model evaluations over different ensemble sizes for two of the optimization algorithms we have, both TECI and ETKI. And this is for a target RMSE of 1. And from this, we can see that there is a trade-off between having a small ensemble size where we have worse gradients, worse gradient approximations, we need more iterations, versus if we have a larger ensemble size, we have better gradient approximations and fewer iterations. So from this trade-off, we can find the ensemble size that gives us the least number of forward model evaluations. So in this case, ETKI would reach 7 versus TECI would be at 9. And so this is the way that we're going to determine how to pick the ensemble size for each one of the methods. So this is kind of just a schematic to show what we do for each of the test problems. And then I'll show one of these for the actual test problem that we have. Um, okay, so now I'm going to go into the example problems that we use to test each of these methods. The first one is going to be based off of the Lorenz 63 set of ODEs. So here we're looking at three differential equations that rely on three parameters, sigma, rho, and beta. And if we set the parameters to 10, 28, and 8 over 3, we get this really nice butterfly attractor. And so the goal of this problem is that we want to find the parameters rho and beta from statistical data. And so what we're going to do in this case is we're going to run through our simulations for a given period of time tau, and then the statistics that we calculate from this are going to be our observations. So first we're going to calculate the mean of the three states, then we'll calculate the variance of the three states, and lastly we'll calculate the covariance of the three states, and this is going to be our observations y. And from this, we're going to try and learn rho and beta. Okay, so for picking the optimal ensemble size for this problem, if our target RMSE is 1, we look at the average number of forward model evaluations for each method for various ensemble sizes. So for each one of the methods and each ensemble size, we run 100 experiments, and then we average over the number of model evaluations that it took for each method to reach the target RMSE of 1. So this is all an averaged result. And as we see from this, we see that the iterative ensemble Kalman filter takes 6 ensemble members in order to reach its optimal ensemble size versus Techie and ETKI have an optimal ensemble size of 10. So these are the ensemble sizes that we're going to use to compare the number of forward model evaluations that each algorithm takes to reach the target error. And so now going into the results. So here we're looking at a bar chart of model evaluations versus different RMSE targets. So in this first case, we're looking at an RMSE target of 1. And to be clear, the lower the bar, the better. So we want the algorithm to have the least number of forward model evaluations. And we see from this that UKI takes the least number of model evaluations compared to all the rest of the methods. And so if we were to look at now how each of the methods did in capturing the true parameters, this is a two-dimensional plot showing values of rho and beta, where we have slices of the loss function on the top and on the right. And then in the center, we have a contour plot showing the posterior distribution, with X showing the posterior mode. And then the dark gray dot is showing the true values of rho and beta. And then all the color dots are examples of the solutions that each of the ensemble methods were able to achieve. So we can see that each ensemble method was able to very closely get to the true parameters for this RMSE. We can also wanted to see how the ensemble methods would do if we change the RMSE targets. So if we increase the RMSE by a little bit and go to an error of 1.1, this would mean that the solution is a little bit worse than the solution we would get before. We still see that UKI does the best out of all the methods. And then on the right-hand side, I'm showing each of the ensemble methods, their parameters that they were able to get to for this target RMSE. And then we do this one more time, so we increase the RMSE a little bit more, and we still see that UKI does the best out of all the ensemble methods. I'd also like to note that the iterative ensemble Kalman filter does the next best, and then Techie and ETKI after that. Okay, so before I move on to the next example, I'd also like to note that the gradient-based method, Levenberg-Marquardt, did not reach the RMSE targets that we prescribed for this problem, so I didn't include it in any of the results on the page. This is really just to showcase that, that it wasn't able to reach the desired level of accuracy that we want for this problem. Okay. The next example problem that we have is based off the Lorenz 96 system. So here we're looking at a set of ordinary differential equations And ZL is the ELF coordinate of the current state. And then these set of equations rely on this forcing phi. So what we're interested in is we want to find the forcing phi from statistical data. So for this particular example, we're going to just find a constant forcing of 8. And so as we see, as we change the coordinate, the forcing stays constant. And we can use this to run through the set of equations. And then here on the right, I'm showing a Hofmahler diagram of a value of the state over a given period of time. And then the spatial index is on the y-axis. And as we can see, we see these waves propagating through the time series. And from this information, we can calculate again some statistics. So for our observations, we're going to calculate the mean of the 40 states and the standard deviation of the 40 states. And we're going to use that to try to then estimate the forcing phi. Okay, so now to go into the results for this problem. We find that UKI again does the best out of each of the methods for all the target RMSEs. So it takes the least number of forward model evaluations. Then we have the iterative ensemble Kalman filter that does second best, and then ETKI and TECI do third and fourth best. And so again, if we try to now look at the solutions that each of the methods were able to get to, the true forcing is 8, and we see that all the ensemble methods were able to get to a very close estimate of the true forcing. I'd also like to note that right, this loss function, there's a lot of noise in this loss function, which makes it a very difficult problem. And for our gradient-based method, the Levenberg-Marquardt, it does, again, get stuck when performing the optimization. So it's not able to achieve the same level of accuracy as the rest of the ensemble methods. And so it's really dependent on the solution that you use to initialize the method. So this is just one example, but it maybe like gets stuck in this area because of the noise in the loss function. Okay, so the next example problem I'm going to talk about is I'll refer to as the modified Lorenz 96. It's going to be building off that last example problem that I showed. So again, we're looking at the Lorenz 96 system, where ZL is the L coordinate of the current state, and we're really interested in finding the forcing phi from statistical data. But in this case, instead of phi being a constant forcing, we're going to make it a spatially dependent forcing, where phi is going to be a sinusoid. So the orange line is the forcing from the previous example, and now the dashed line is going to be the forcing for this example. So again, we can use this forcing to run through our set of equations, and then we'll produce a time series. Again, this is a Hofmahler diagram showing the value of the state given each of the spatial indexes. And then we can see here that the really large state values are associated with the large forcings versus the lower state values or the lower variability is associated with lower forcing values. And this is because the larger the forcing, the more chaotic the behavior of the system versus the smaller the forcing, the less chaotic. But I just, yeah, wanted to note this. And again, for our observations, we use the average of the 40 states and then the standard deviation of the 40 states for our data. And then now I'll go into the results of how each of the methods were able to approximate, to estimate the forcing phi. So in this particular example, we see that the iterative ensemble Kalman filter is able to surpass UKI, requiring the least number of forward model evaluations. And then actually, as we increase the RMSE target, UKI tends to do worse and worse comparatively to the rest of the methods. And this is due to the fact that UKI has a fixed number of ensemble members. For this problem, the dimension of the parameter space is 40 because our forcing is as a 40-dimensional forcing. So the number of parameters UKI needs is 81. And the other ensemble methods are able to use smaller ensemble sizes and then get to the same target RMSE with a smaller computational cost. And so if we now look at the solutions, each of the methods we're able to uncover, we see that the dark gray dashed line is the true forcing, and then each of the methods were able to capture the forcing behavior quite well. Um, and uh, and then lastly, I'd like to note that again, the gradient-based method did not reach any of the target RMSEs. Okay. Now I'm going to go into our last example problem. So again, we're kind of building off of the same example again. We're dealing with the modified Lorenz 96 system, but now we're going to introduce a neural network into the framework. So again, we're trying to estimate this forcing phi. Given information from the state. So in this particular example, again, we're going to have a sinusoidal forcing, but we've now increased the state dimension to 100. The size of the data is going to be a bit bigger. But again, we can, right, we run through our set of equations to create a time series, and then our statistics are again going to be the mean of the 100 states and then the standard deviation of the 100 states. But instead of trying to estimate the forcing directly, where we're trying to estimate each value at a given coordinate, we're going to approximate the forcing using a neural network. And in this scenario, we want the network to approximate the sinusoidal behavior. And in order to do that, we need to learn the weights and biases that go into the network that will produce this behavior. So the idea of this problem is that we want to learn these weights and biases given the statistical information that we have of the system. And for this particular problem, we have 61 weights and biases, so the dimension of the parameter space is 61. Okay, so now to go into the results for this problem, we see that UKI does require significantly more model evaluations compared to the rest of the ensemble-based methods. And we also see that Techie and ETKI were able to reach the least number of forward model evaluations given the different RMSE targets. And this is partially due to the fact that the iterative ensemble Kalman filter does require a pretty strong prior in order to be successful versus Techie and ETKI. They don't need to have as much prior information in order to still get to the solution. And so the iterative ensemble Kalman filter does struggle a lot more on this neural network problem versus the other two. And then if we look at the solutions that each of the methods were able to uncover, again, we see that they were able to capture the sinusoidal forcing very nicely. And we see that in this example compared to the previous example problem, that all the solutions are smooth. And that's because we use a hyperbolic tangent activation function within our neural network that enforces smooth solutions. And then again, lastly, our gradient-based method did not reach any of the RMSE targets, so it's not included in any of the slides here. Okay. Lastly, I'd like to summarize and conclude the main results from this work. So again, our main question was which ensemble-based method is best for learning parameters from statistics? We found that UKI is best for problems with small parameter space dimensions. So for those first two example problems that I had showed, UKI had done the best on them because of the size of the parameter space. But unfortunately, it does not scale well with the size of the parameter space. In the last two example problems, as the size of the parameter space grew, UKI continued to do worse and worse, or relatively worse and worse. Then we have ETKI and Techie, which are best for when we have uninformative prior information, and they're also very robust. So for these methods, we found that they can estimate parameters even with really weak priors. One example that I wasn't able to show in this presentation is how we have in the neural network example, we do try to prescribe a pretty informative prior, but we do also have an example where we have a very uninformative prior, and ETKI and Techie are still able to uncover the solution for that, which is very impressive. And we also found that they're the most robust for climate science problems. So they're successful on all the example problems that we had tested. And then lastly, we have the iterative ensemble Kalman filter, which does generally perform well, but it does require a strong prior. um, uh, which might make it not as robust for climate science problems. And then lastly, we have the Levenberg-Marquardt algorithm, which is never able to hit any of the target convergence criteria that we prescribe. And then the reasonable RMSE targets are too low for it to reach. Um, and then lastly, I'd like to conclude on that the ensemble methods are really the right choice for learning parameters from statistics. And other algorithm enhancements like localization and inflation were not considered in this work. So there are other ways to enhance these algorithms to make them perform even better. And we're hoping to kind of investigate this in future work. Um, with that, I'd like to conclude. Thank you so much for listening. And there is a preprint of this work available now on the archive. So if you'd like to scan the QR code, you can go ahead and read that. And then my email is at the top. Thank you so much.
Okay, great. Yeah, thanks for the great seminar, Rebecca. I don't know how to do clapping and how do we do clapping and oh, here we go. Virtual clapping. There we go.
Well, thank you so much.
Right. We have quite a bit of time for questions. So are there any questions? So feel free to just unmute or raise your hand or type it in the chat. Let me open up the chat if I can. The chat go.
Hey, I have a question. I'll put it in the chat if you could read that.
Let me see. Sorry, I'm trying to find the where did the chat go? Oh, do you want to just ask it since you're off mute?
Yeah, sure. Hey, Rebecca, it was a really nice talk. Can you comment something about the square root formulation where you do not do an optimization and the update is done using a Kalman matrix term?
Uh, yes, if I'm understanding your question correctly, you're talking about uh 1 minute. Uh
There's a paper by Whitaker in 2002.
oh, um, are you talking about the ensemble transform filter, or are you maybe you're talking about something else?
Yeah, it's something else. So all of these does an optimization procedure, right?
Yes.
Yeah, so so you see this Kalman gain. So there is this formulation called ENSRF, uh,
Okay.
and so that does not do an optimization. The data assimilation is done using Kalman metrics term multiplying the difference between the observed and the averaged forecast observation. And so I was wondering if you had done anything similar and if you could comment on that.
Right. Okay. I actually haven't. So the reason that we use these specific methods in this study is because they all require very little tuning. And also because we wanted to kind of investigate these optimization methods first before we did anything that gave us like an uncertainty quantification,
I see.
because we kind of wanted to start like simple and then, but we're hoping to, and this is some work that I've already been doing with some of our collaborators on investigating more widely on UQ-based methods and how they do for calibration.
Right.
So this is something we're looking at the moment, but wasn't considered in the study.
Okay. And one more question. Uh, Do any of these methods use an adjoint?
No, so none of the ensemble methods use an adjoint, and so
Okay.
which yeah, so which makes them really easy to use just straight out of the box.
Right.
For the gradient-based method that we use, the Levenberg-Marquardt, you can use an adjoint for that.
Okay. Can you comment on some possible machine learning approaches that will make these things easier?
Um, I'm not sure if they're this is a good question. I'm not too sure on ways to use machine learning to enhance the algorithm's performance. There is an algorithm, it's called on ESMDA, or like on small the ensemble smoother with multiple data assimilation. And um, uh, there was a study done where they tried to use machine learning to make better approximations of the covariance matrices in order to improve the update that was being made, which seemed to help. But I haven't seen that implemented in any of these methods.
Yes.
So other than that, I'm not too familiar with other machine learning techniques that can enhance the algorithms.
Right.
But yeah.
Yeah, I have not seen it either, but so I just want to know what your take on that is. Yeah, but great talk, Rebecca. Yeah, thank you.
Oh, yeah, thank you so much.
So I see Andy Salinger has a question. Andy, do you want to unmute and ask it?
Yeah, sure. Hi, Rebecca. Great talk. Very topical. Thank you.
Oh, thank you
I
so
was
much.
wondering how you see these scaling to when we have thousands or tens of thousands of parameters in a neural net that we're trying to train, such as, an example is trying to have an emulator for cloud microphysics on a column that may have, very large neural net trained it with a climate model. Do you see these things scaling to that size of a problem?
Yeah, this is a really good question. And there's a ton of work that has been done and is being done on ways to make these more scalable. So one of the things that I didn't really talk about is localization and covariance corrections. This is a way that drastically is able to reduce the number of ensemble members that you need in order to reach these target RMSEs. And so in all the example problems that I showed, the ensemble sizes need to be larger than the size of the parameter space. But if you were to use kind of these algorithm enhancements, you can reduce the ensemble size to much smaller than the parameter space, which then gives you the ability to try to work on these problems where you have like tens of thousands of parameters. So it is definitely possible, and there is ability to scale, but I think there's definitely some more work that needs to be done to have them working on these like really large scale problems.
Okay. Oh, great. Thank you.
Other questions? Yeah, so I had a few questions. So I guess the kind of Andy's question maybe made me think of this, but there's also the case where like you're given a very limited ensemble size, right? Because you can only run a few climate simulations, let's say. And so then you wouldn't be able to pick that, right? And so that would be an interesting study, like for a fixed, relatively small ensemble size, which is the best method, and that would probably depend on how many parameters and how complex the model is.
Right. Yeah, exactly. And there is a study that we do mention in the preprint that we have. It's not on ensemble-based optimization, but it's on derivative-free optimization methods. And they kind of take this approach that you're talking about, where they have like a fixed computational budget, and then they see
Yeah.
like which algorithms do the best. So like how, which ones are able to achieve the best level of accuracy. So we kind of have like slightly different criteria that we're looking at, because like in this case, we're looking at, okay, like for a fixed accuracy, what's the computational cost? But in their study, it's like, okay, we have a fixed computational cost. What like level of accuracy can we achieve? So I think it would
Yeah.
definitely be interesting to see that.
And then when you were showing your results, like with the bar charts, it seemed to me like the method that required the most ensembles required also the most iterations. Like for the first problem, it was the green one, which I think you showed, or is that I mean it's just that if you go or no, sorry, if you go maybe if you go to the last example, or the one of the last, the second to last or the last, um, the one where the
This one?
yeah. I mean it's kind of interesting. I mean I because like I think of, because the UKI requires the most ensemble members, right, for this problem, because there's a lot of parameters.
Right.
And it's
Yes.
just I would think that like more ensemble members would improve things, and it seems like it has the opposite effect. Um,
Yeah. Yeah,
which
that's
is it?
yeah, this is also, I think, pretty interesting to us. So, we've kind of found that there's kind of like a minimum number of iterations that each of the methods need in order to converge. And so, Yeah, because UKI like requires such a much larger ensemble size versus the other methods, it kind of is at a disadvantage because it still needs to do at least like a few iterations to kind of reach the target error. However, we did find that the iterative ensemble Kalman filter in general needs more iterations than the other methods, but it is able to get away with a slightly smaller ensemble size than the other methods, which makes it still competitive in a lot of these examples that we show.
Yeah, okay. Jason has a question. Unmute yourself, Jason.
Yes, hello. Thank you for your talk.
Oh yeah, thank you so
So,
much.
yeah, I, if I'm recalling from your Lorenz examples, the dynamics depend linearly on the parameters that you're estimating. And I was
Okay.
wondering, how does this method perform for parameters that non-linearly influence the dynamics? So instead of just having a beta times some of your other coordinates, having a beta squared or something of that sort.
Mm, if I'm understanding your question correctly, so you're asking like, what if the relationship with the parameters is like nonlinear given the output?
Yeah.
Yeah. So I would like to point out, so all of these problems like are like nonlinear. However, I would like to specifically point out the neural net example because so in this particular case, we're estimating the weights and biases of the neural network. And then the solution that I'm showing you is the like uncovered forcing that like the neural network puts out, so that's like the neural network solution given the weights and biases that we estimated. But estimating weights and biases is extremely nonlinear problem. There's many solutions that will kind of give you this same similar behavior. So estimating them is very difficult. And I would not consider this a very linear problem.
Okay. I didn't realize that you were estimating the weights and biases. I thought you were estimating the forcing output, that last term in these equations.
Yeah, for the previous example, we do estimate the forcing directly. So in this case, we're trying to estimate each value of the forcing given its coordinate. But yeah, so for this next example, what we're trying to do is you're trying to estimate these 61 weights and biases that will give us a network that approximates this sinusoidal forcing. Um, yeah. It's a very hard
Cool.
problem to achieve. Yeah.
Yeah. Thank you.
Thank you for your question.
More questions?
Rebecca, quick question. So in this, do you form the matrices explicitly or only the matrix vector products?
Um, by matrices, which matrices are you referring to?
So for example, the Kalman game.
Yes. So the uh, let me go back to the solution here. Right. So we do calculate the Kalman gain explicitly. So we're using the statistics from the ensemble to make an approximation of this. Um, so we do calculate it explicitly.
Okay, thank you.
There's another question. I don't know. MF Holst is the username.
Yes, it's Micah.
Oh, hi. Go
Hi.
ahead.
Yeah. Yeah, great talk. I just did some really similar work, so this was really interesting to me. And for the work that I did, I used the Ensemble Kalman sampler with maybe not always great results. So I was wondering if, I know you didn't use it here, but have you used it in the past, and how, in your opinion, how does its performance compare to these other methods?
Yeah, this is a good question. So I'm not super familiar with the Ensemble Kalman sampler. I have read the paper, but I haven't implemented it in practice. However, because it is like a UQ based method, it's a little bit more difficult to compare to these like optimization based methods. However, me and my collaborators were very interested in comparing different UQ-based methods to see which ones might be better for this problem. So it's kind of like a next step to doing this work. But that's also kind of like, I don't know, I feel like it opens a big box of like different things that you could take a look at, because with UQ methods, there's a lot of different criteria that you could say makes a method better or worse, right? Like depending on the distribution you're trying to approximate. Yeah, for this study, the reason we didn't use any UQ-based ones was because we wanted to just like strictly focus on optimization. However, I think it is really important to explore. And there's tons of other UQ-based ensemble methods too, like the ESMDA, the iterative ensemble smoothers. So I think it would be really interesting to do a study on that.
Okay, cool. Thank you.
Cliff, there's a question from Cliff, or maybe that's a username. I don't know. But do you want to ask it? Oh, sorry. Okay, so the question is there software available for the ensemble methods? I'm not familiar with these methods, so sorry if it's a basic question.
Oh no, that's a wonderful question. I do have a public repo up on my GitHub. It's called the EKI race. And it should have a file with all the different methods that I used for the study. And they all include regularization. So you can, and I tried to design them in a way where they kind of mimic the SciPy optimized algorithm. So hopefully they can kind of just work right out of the box if you have a simple model in Python with some parameters that you're interested in estimating.
Then there's a comment that there are some great Julia packages that implement them as well.
Oh yes, yes. I should also mention the Julia packages are it's called the Ensemble Kalman processes, and I also helped put in one of these methods, the iterative ensemble Kalman filter. They call it GNKI in their docs, but that's also I helped implement that, and then there should be the EKI race folder where you can see all these example problems kind of implemented in practice. So you can also take a look at that in Julia.
So maybe I'll ask the last question. So I was just curious, this is like the motivation here is climate, but have you actually tried to apply this to climate data yet, or this is kind of the next step?
Yeah, this is a next step I'm also looking at. A project that also has been recently submitted for publication. It's a auto-differentiable general circulation model in Python. We call it JCM. And
Uh-huh.
so I helped work on that. And so one of the things we want to investigate here is, what time scales do we need to estimate certain parameters, where gradients can be beneficial to use, where maybe these ensemble methods are able to be used. And so it's a nice framework because it's not as big as these really like huge climate models, but it's a nice like
Uh-huh.
next step to take to try and do this for real.
Yeah, it sounds like that code could be useful for people who are developing or assessing other methods too, if it's a relatively small one.
Yeah, it's a really great code base. It's also up on GitHub under the Climate Analytics Lab.
Oh,
Yeah, and the version 1 we just came out with in December.
okay, nice. Okay, well, we're basically at time. So thank you everyone for coming.